Deep learning models have proven to be incredibly useful in our daily lives, but they can be tricked into making incorrect predictions with high confidence. In this podcast episode, I'll be talking with Pooja, who has done extensive research in the area of adversarial attacks on multivariate time series forecasting. Welcome to the podcast, Pooja.
Thanks for having me, Luke. It's a pleasure to be here.
Great. So at a high level, what was the main purpose of your paper and what are its main contributions?
At a really high level, the main purpose of the paper was to assess the vulnerabilities in deep learning models and to come up with defense strategies for attacks that an adversary carries out against these models. And the key contributions of my paper I would start off with like the development of deep learning models to first solve some tasks so that we can then move on to attack it and prove how easy it is to throw these deep learning models off so that they can make incorrect predictions with utmost conviction. Because it's easier to have deep learning models that tell you, hey, I think this is the answer, but it's worse when they say, I think this is the answer with like 99% confidence, right? You wouldn't want them to do that. So I wanted to prove how easy it is to be able to do that with deep learning models, and that's like the adversarial attacks part on a working model. And then to also develop defenses, we just didn't want to stop with saying, hey, it is a threat. We also wanted to prove that this can be mitigated with like work in this area. So to come up with defense strategies for the attacks was like another contribution of our paper, and to prove that these attacks and defenses work like they should. And we can talk about it more in the podcast. And I think another novel aspect of my paper is proving that the attacks are indiscernible to the human eye, especially since this is time series data and not a lot of work has been done in this field. I think another contribution of my paper was in showing that the attacks cannot be detected by humans, and it is easy to poison the model and get away with it. And hence the consequences are going to be severe, right? The repercussions are like more when you're not able to prove that the model has been attacked. So that is another contribution. And the last contribution of my paper is just transferability, to prove how easy it is to do this with any deep learning model. And I think the upside of transferability, though, is the attacks are transferable and so are the defenses. And I think the underlying or the bottom line of this paper is to emphasize on the need for defense techniques in order to mitigate against the adversarial attacks.
Interesting. Makes a lot of sense. Great. So let's go into some of your background. What university degree do you have, or are you currently pursuing?
I just graduated from my master's in computer science at San Jose State University. And when I said just, I meant it happened this May 2024. And I'm now doing data science and artificial intelligence under the Faculty of Mathematics in the University of Waterloo.
Interesting. And was this paper a part of your research at your university, or was it a part of your work?
It was part of my research at San Jose State, and yeah, it was needed for my degree to be completed. Yeah, it was part of my degree requirements.
All right. And did you present this paper at a conference?
Yeah, the paper was accepted to the 16th Annual Conference of Prognostics and Health Management, PHM, in Nashville, Tennessee. I think it happened this November from 11th to 14th, and we did present our paper in that conference. Yeah.
And how did you get into this type of work?
Well, honestly, I think I've always been a person who enjoyed learning by drilling down and breaking down a concept. So I'd go to the crux of it and try to build up from there, and it helped me remember things better and it lasted longer. And I think when I had an opportunity to carry out research at San Jose State, it didn't feel like it was something that I had to take efforts to do. It just felt that it came easy, and to manage it with like my coursework wasn't hard. So I think I didn't feel like a fish out of water. It just spoke right to me. Like I think it was in my wheelhouse. So yeah, I enjoyed doing it, and I continued doing it for like a year and a half. And yeah, I guess that's how I got into this type of work.
And how did you come up with the idea for this research paper?
The idea for this research paper, I think I was intrigued by the field of responsible AI and AI governance when I first attended the 2023 Women in Engineering conference at San Jose State, because we were hosting it. And there were like a couple of workshops that I attended where the speaker spoke about how adversarial attacks are a problem, especially in the field of computer vision. And one of the speakers there talked about self-driving cars and how you can poison like the edge pixels of like say a stop sign and trick the deep learning model that governs the self-driving car into thinking that the stop sign is actually say a 65 mph speed limit on a freeway. And if you can do that, then the consequences are going to be severe. And I remember coming back home and researching about the impact of these attacks in the image domain, and especially with, I think, the rise of ChatGPT and other sequence to sequence models. I think I somewhere pivoted and I was looking into time series forecasting tasks, and I realized that not a lot of research has been done in the field of time series forecasting. And I think I just wanted to see where it goes and, try to employ known algorithms that have been tried and tested in the image domain in the field of computer vision, and try to extrapolate those insights and see if they would work in the time series task, in the time series domain.
Very interesting. Great. So let's go into some questions about the paper. What is time series forecasting, and what are some common applications for it?
Time series forecasting is when you try to predict future values based on past values. And when I say future and past, I mean there is a temporal component in it, right? So you have the same features that were recorded at a previous period in time, and you're trying to predict or model those features and how they would change in the future. So that is what time series is. And so it might be the applications for it might be weather forecasting, or in our paper, we used the remaining useful life prediction of equipment. So we used hard disk drives. So that is like one application for it. And it can be multimodal. You don't really need to be dealing with even numeric data, because if you're recording, like say, the growth of a human brain over the years, then that would just be you're pushing time through the image, right? So you have X-rays and you're monitoring the X-rays throughout the years, so multiple time steps. So yeah, it could be any kind of data, but it's just it needs to have the temporal component in it. You're looking at the past values to make predictions into the future.
Could you explain what is multivariate time series forecasting?
Sure. And I think this is a great question, because it's literally there in the title of the paper, right? We're claiming that we are dealing with multivariate time series tasks. So there are two different types of time series. One is univariate, where your independent variable is just one, and hence the name uni. So it could be as simple as measuring the growth of like a tree based on over the years. So in that case, your dependent variable is only the growth of the tree, and your independent variable is time. But then in multivariate time series forecasting, you have multiple exogenous variables that contribute to the dependent variable. So in this case, let's say it's the growth of the tree, but the growth of the tree is not just dependent on time anymore, but say it also depends on the amount of water or the amount of sunlight or the pH of the soil, etc. Right? So you would want to log those and keep track of it as time passes, and then use that to model what the future growth of the tree is going to look like, or how it's going to be affected. So that is what multivariate time series is, when you have multiple independent variables contributing to the dependent variable.
And so what has led to the transition from traditional time series forecasting methods to deep learning architectures, and why is it a double-edged sword?
I think traditional time series forecasting was needed when time series problems started out, and statisticians were really enthusiastic in coming up with a way to predict the future based on the past, and there wasn't a lot of data back in the day. But then with the proliferation of big data and compute, I think deep learning architectures were sought after to solve this task of time series forecasting, because they just perform better. And I think it is a double-edged sword because of, I'm going to circle back to where we started with the vulnerability of deep learning models and how easy it is for you to perform adversarial attacks on them. And so if the upside of using traditional time series would just be that you cannot do something like this in traditional time series forecasting tasks. Whereas when you're using deep learning architectures and it's so easy to thwart the model's predictions, the repercussions are going to be severe. And which is why it is a double-edged sword. It helps speed up computation, it's more accurate, but it also needs to be secure. And I think that is why it's a double-edged sword, and it's imperative that we work towards fortifying these deep learning models.
What are the different types of adversarial attacks, and how do you classify these attacks based on ease of access and the attacker's goal?
Okay, there are 4 different types of adversarial attacks, and you have 2 each into each of those categories that you just asked me. So based on the ease of access, you would classify them into black box attacks and white box attacks. And what that means is white box attacks are one of the attacks that we explore in the paper. Actually, it's the only one that we explore in the paper, and that is when you have access to the model's gradients and the input data. Whereas in black box attacks, you don't really have access to those bits of information. So you would treat the model as an oracle which spits out something given the data, and then you'd only have the model's behavior to work with, and then you have to work your way around how to perform an adversarial attack in that scenario, because it's a little bit more tricky than white box attacks when you have direct access to the input data and the gradients that are used to train the model. Whereas based on the attacker's goal, however, if you are classifying adversarial attacks, they would be differentiated into 2 as targeted attacks and untargeted attacks. So in targeted attacks, the goal of the adversary is not just to make the model predict incorrectly with high confidence, but they also want to make sure that it predicts a specific output or a specific class that is wrong. So for example, going back to the self-driving cars example, you don't want it to predict it as the stop sign, but you don't want it to predict it as a red light either, because then the output would be the same, the car would stop. But if the adversary really wants to cause a catastrophic event or an incident to happen, then they would have to predict it as like a green light or something which says a 65 mph speed limit that's common on like the United States freeways. So I think that's what the targeted attack is all about. You don't just want it to classify the input incorrectly. You want it to be very specific in saying, hey, this is a green light with like 95% confidence, because only then will the actual malicious intent of the adversary even be satisfied, right? Whereas in untargeted attacks, though, it's a lot easier in that you only have to make the model say that it isn't what it is with like high confidence, but you don't really care about what the incorrect prediction is. So those are the different types of attacks. And just to clarify, like in this paper, we carry out untargeted white box attacks on all the data sets.
Very interesting. Great explanation. So could you explain the types of defense techniques and which ones did you decide to employ in this research paper?
Sure. Commonly, there were three types of defense techniques, generally speaking, in like a broad manner. So the first one is model hardening, where you try to change the inputs that the first one is model hardening, where you try to change the architecture of the model in order to be more robust to these type of attacks. So you would incorporate changes to the model architecture during the training process and try to make it learn a more robust underlying distribution, so that when you do feed it in with like poisoned examples, it's able to recognize and learn like a more robust distribution and not be fooled so easily, if you will. But that's just one type of adversarial defense techniques. And the other one is input pre-processing, where you would pass the input through like a data pipeline, which would scan it for, like, say, malicious inputs or modifications, perform sanity checks, and feed it into the models with the hope of feeding in clean data, so that the model isn't fooled and you're not really doing anything to the model architecture there. And the last, but also one that's most commonly employed because of how naive it is and how easy it is to like test out, is data augmentation based approaches, where you feed in the model with poison samples in the hope that it learns to train over like the poison examples as well and learn the correct predictions, so that it's more robust to these poisoned examples when it sees them in the future. So, and in our research, we did data augmentation based adversarial training and model hardening. We did not do anything similar to data pre-processing, because that's, you're not really dealing with ML there. You're going more into, you're stepping into data processing, and that's really not deep learning related, but it is something that people can employ to make sure that you're feeding in clean data to the model. So yeah.
Could you describe the two data sets that you used in your research, and where did they come from, and what are you predicting?
Of course. So the first data set that we used was a toy data set. It was from the University of California, Irvine repository, which just predicted household power consumption. So given like the voltage and current in amperes, and say the readings from like a couple of meters, you would try to predict what the power would be given the past values of these features. And the goal of, I think it had like 2 million rows, and it recorded like electricity data for a period of 4 years from, I don't even know, I think 2006 to 10, if I'm not mistaken. But then I think the goal of using this data set was to perform a sanity check of our algorithms to make sure if they work as they should, because like I told you, I used algorithms that were tried and tested in the computer vision field, and I extended them to multivariate time series tasks. So the first part of this research involved checking if this was even possible, and I think we needed like a smaller data set to perform that check, and that was the reason for employing the electricity data set. And the second part of the research, where we try to prove how easy it is to transfer these attacks and defense strategies to other data sets, involved using the time to failure prediction of equipments. So that was a much larger data set that we scraped off from the Backblaze website. So Backblaze is, and we used, I think, the Seagate model of hard disk drives, just because there was prior research in the Seagate family of RUL prediction, and it was easier and helped us focus our efforts on building the attacks and defense strategies instead of wasting our time on data pre-processing or building like an architecture for it. I mean, we still did come up with like an encoder decoder LSTM for it, but it the reason for choosing Seagate from Backblaze was just to prove the transferability of these attacks and how easy it is to extend this to like much larger real world data sets, while also keeping our efforts focused on the goal at hand, which was primarily to attack and defend against these models.
Could you describe the neural network architecture that you used for the household power consumption dataset?
Of course, we used a simple vanilla LSTM, so a long short-term memory architecture. I think we split the data with the usual 80-20 rule, so 80% for training and 10 for validation and 10 for testing. But yeah, it was just a vanilla LSTM network with sequential units. I think we used the ReLU activation function. Adam was the optimizer. And again, like I said, it was a toy data set that only served as a sanity check for our algorithm. So we did not spend extensive time and efforts into coming up with an architecture for household power consumption prediction, because it was a task that people have already worked on a lot. But we also did get like great results after the training, because we did do a lot of experiments. Like we did like k-fold cross validation and like look backs and tweak the parameters in different ways to come up with a best performing model, which would then be chosen to perform the attacks and defenses.
And I know you were just getting into it a little bit, but what type of cross validation did you use and why did you use it?
Oh, since we were dealing with time series data, it wasn't possible to use the classical k-fold cross validation or the stratified cross validation. So we had to use walk forward cross validation in order to maintain the sequential nature of time series data, because it wouldn't make sense for the model to look into the future and then try to predict the past, right? So you wanted to maintain the sequential nature, and so walk forward cross validation helped us do it. So in walk forward cross validation, you'd have like say the first X samples in your training set and the remaining would be in your validation set. And then you just increase the window size in the next iteration to include a little more from the validation set into the training set, and so on and so forth until you reach like the entire data set.
What metric did you use to compare your models and why?
We used the RMSE metric. If you're just talking about like the training phase, we used root mean squared error because it is like the most commonly employed metric for the type of problem that we were dealing with. It was easier to use it in terms of like benchmarking. It helped us benchmark against state-of-the-art models better because a lot of people use it as a metric, and that was pretty much the only reason in terms of the metric for the training process. And I think we used RMSE as a metric for the attacks and defenses as well, but I think there we focused more on what percentage the RMSE actually improved or worsened by. Again, for benchmarking purposes, helped us benchmark better.
I see. Could you describe the neural network architecture that you used for the hard disk drive dataset?
Sure. So for the hard disk drive dataset, we used, because the vanilla LSTM model wasn't really working well, since it was a sequence-to-sequence task, and we came up with like a slightly different architecture because we still wanted to keep the architecture simple and not go into a lot of complications there, because the task at hand was to deal with the attacks and defenses. And so we used the encoder decoder LSTM to handle like the sequence to sequence predictions of the remaining useful life task. And if I can just go into how, I don't know if you plan on asking me that, but if I can just go into how remaining useful life works and what we're actually doing there, I would love to right now. Thank you.
Yeah.
So the thing is, prognostics and health management, which is where this which is the conference, which is also the title of the conference that our paper got accepted into, is a vital area in monitoring and maintenance, where you try to predict the remaining useful life of equipments to identify when they would fail. So traditionally, they started out with something called reactive maintenance, where if an equipment fails in the industry setting, people would go in and replace it after failure, and this is going to disrupt the normal flow of operations. And then they came up with something called preventative maintenance, where they replaced it well before failures, and this led to like wastage of resources, right? You don't want to replace a fully functioning hard disk drive or lithium ion battery or any other equipment for that matter. And so with the advent of deep learning models, again, you had data, you had compute, it was a time series task. And so they decided to come up with predictive maintenance, where they tried to predict the time to failure of disks, so that they can then go in and replace it just before failure, and also hopefully set like a downtime so that the normal flow of operations aren't affected. And that is the task that we're trying to solve. And I just wanted to get into the data set a little, because a lot of effort went into generating the data set for this task, because we didn't have it custom made. And we had to, so what we did have was from the Seagate model, or the Backblaze website, was a data set which indicated when the disk failed. So there was just a column which said failure 0 or 1. So did it fail at a particular day, given these smart features, 0 or 1? But then in order to model it as a multivariate time series task, we had to use this data and come up with like a different data set that had like another column which said remaining useful life. And what we essentially did there is we worked backward, and we took the data from like the time to failure. So say a specific hard disk had failed, or like say today, and then we had like data that said that it hadn't failed the previous days, and then we had to work backwards and compute the remaining useful life. So yesterday would have the RUL value of like 1, whereas today would be like 0. And then we created like another data set with like the specific RUL field, where we computed what was the time to failure of the disk, and then we modeled it as a multivariate time series problem. But I think I deviated a lot from your initial question. It was needed to explain why it is a sequence to sequence task, because the one that's available on the internet, it's not really sequence to sequence. It's not even a multivariate regression problem, but we had to change it to one in order to work with it as a multivariate time series problem. So to answer your question again, though, it was an encoder decoder LSTM, because they handle sequence to sequence tasks pretty well.
That makes sense. All right, and now we can go into some questions about the attacks and defense strategies. So the first question is, what is the fast gradient sign method to perform adversarial perturbations?
The fast gradient sign method was something that was proposed by Ian Goodfellow in the image domain to attack the pixels in an image. So, and it was actually one of the very first algorithms that was even proposed. And it was when people even figured out that this is a problem with deep learning models. And what this essentially does is it creates a set of adversarial inputs that will throw off your model. And how it does this is it just adds noise or perturbations to the actual examples in the direction of the sign of the gradient. And as you know, in neural networks, backpropagation and essentially how they work is done by calculating the gradient and then moving in a direction which minimizes the loss. Whereas here you're using information that maximizes the loss, and you're adding it to the actual training example. So to the naked eye, it doesn't really look like anything has changed at all, and the samples still remain the same, especially because you scale this information that maximizes the loss by a perturbation magnitude, which is also called epsilon. And epsilon is usually said to be very small. So to the naked eye, it doesn't look like anything bad is even happening, and it looks the same. A human would still make the right predictions. But to the model, though, it makes all the difference because it affects how fundamentally it learns to predict using the backpropagation technique. So imagine, like, say, for example, you have like a child that's trying to paint, and you have like an adversary that's trying to destroy the painting. So what FGSM basically does is it tries to identify where can I cause like the maximum damage with like the least effort. So that's what it does when it tries to find something that maximizes the loss, and it also scales it by the perturbation magnitude, which is very, very small, which is why people cannot detect it using the naked eye.
Great. And what is the basic iterative method for adversarial perturbations?
The basic iterative method for adversarial perturbations is just you applying the FGSM attack iteratively multiple times. So you would have an alpha value instead of just epsilon, which controls how many times you attack the model iteratively and perform FGSM. So no doubt about it, it's obviously like a more powerful attack than the fast gradient side method because you're applying it many, many times. And the purpose of us using it was to check if this, in fact, did throw off the model more and cause worse predictions, and how much were the predictions off by for the same magnitude of perturbation.
How could you use data augmentation-based adversarial training to defend against these types of attack vectors?
Yeah, like I mentioned earlier, adversarial training is like one of the techniques used in defenses, and data augmentation based adversarial training was also one of the first ways in which Ian Goodfellow and his associates worked to defend against the attacks. And it is really naive when you think about it, because all you're doing, and it's not very efficient to be honest, because all you're doing is you're generating adversarial examples during the training process itself, and you're feeding it into the model in the hope that it tries to learn over the correct labels or the correct predictions given the poisoned examples itself. And it is one of like the first methods of defenses. But when you actually think about it though, right, you don't need to guess the perturbation magnitude that the adversary would use. So if the adversary used, like, say, a different set of examples that were generated by a different by using a different value of epsilon or the magnitude of perturbation, then your model is still going to be vulnerable, right? And we used, for testing purposes, we did use like the same epsilon because then it wouldn't make a lot of sense. But it is something that works, but it is also very naive, and we do need to like work on improving it, which is why we work on another defense strategy as well.
How could you use layer-wise perturbation-based adversarial training to defend against these attack vectors?
Yeah, and that is the other strategy that I was just talking about. And it falls under the model hardening defense techniques that I mentioned earlier, where we change the architecture of the machine learning model itself. And Zhang and others had worked on the RUL prediction of hard disk drives, which was one of the problems that we were trying to work with as well. And in order to handle class imbalances and to prevent overfitting in their data set, they had actually come up with this architecture, and they called it layer-wise perturbation-based adversarial training. but it is a model hardening approach where you change the neural network architecture a bit in the hope that it's able to be more robust and learns a distribution that is more robust to adversarial attacks. And so what you do here essentially is you pass in your training process, right? When you train the LSTM network or the encoded decoder architecture, you perform two passes through the model. So in your first pass, you do what you normally do when you train a neural network. So the first, in the forward pass, you would compute the outputs, and in the backward pass or the back propagation step, you would update the gradients. But then in this method of layer-wise perturbation-based adversarial training, you'd go through another pass where in the second pass, you would perturb the gradients. After calculating like the forward prediction, you would perturb the gradients using the adversarial attacks that we mentioned earlier. So say the FGSM or the BIM methods, and then you would perform back propagation to update the gradients through the gradient descent or whatever algorithm you're using again. So you just go through two passes. The first one is similar. Forward, you compute the predictions. Backward, you update the gradients. And then in your second pass, you perturb the gradients and then make the model learn the perturbations as well in the backward pass, if that makes sense. And so that is what we did for the second type of adversarial defense to prove our results. And there was an improvisation or a slight change that I made to this architecture where I came up with two types of gradient updates. I call them DLPAT and SLPAT, D for deterministic and S for stochastic. So I was interested in seeing how the model learns if you introduce some randomness in the weight updates. So in the FGSM and BIM methods, I mentioned something called a perturbation magnitude, which controls how much you're throwing off the model by. So in the deterministic update, I kept it fixed. So it was like the average or between like a range of values. Whereas in the stochastic update, I just used like a random number generator that picked a value between the same range. So I wanted to see how randomness affects the training and if it improves it at all. And that was like one change that we made to the actual LPAT architecture that was proposed by Zhang and his teammates. But yeah, that's the model hardening technique that we used in order to defend against the attacks.
Did you come up with these algorithms from scratch, or did you adapt them from a different domain?
I did. Yeah, I think I've already answered a little bit of that question. FGSM and BIM, I did adapt from Goodfellow's work on the computer vision domain, and it was interesting because I even though I adapted it from an already existing field, I still had to modify it to work for multivariate time series tasks. And so these algorithms or these attack mechanisms are already tools that you can just import as libraries and use off the shelf. And I think the library was called Clever Hans, if I'm not mistaken. But using these for multivariate time series tasks, however, did require a reimagination of the implementation, and I wasn't just able to import the libraries and use them off the shelf. And for the data augmentation, it was just an approach. You didn't really need a lot of implementation there. And for LPAT, however, like I said, I had to implement it from the ground up because we changed our model architecture during the training process itself.
From your experiments, how effective were the two types of adversarial attacks that you investigated?
The adversarial attacks were actually pretty effective. They produced close to a 250% increase on average for both of the data sets. And yeah, it goes to show how something as simple as just changing the inputs to the model can make the predictions go berserk. And I think we did achieve what we wanted to in the end, and show that this is a real problem that needs to be addressed, and why it is so vital to work on building defense strategies for the attacks.
Then also from your experiments, how effective were the adversarial defenses that you implemented?
The adversarial defenses were pretty impressive too. I think we had like a 74% improvement for the electricity data set, and a 95% improvement approximately for the hard disk drive data set. And again, it goes to show how easy it is to implement the defenses as well, and transfer the defense techniques, and why more research needs to go into developing defense for fortification of deep learning models.
And then to go into some closing questions, where might future researchers be able to build upon this work?
I'm sorry, can you say that again?
Where might future researchers be able to build upon this work?
Okay, so you're asking me about the future works part of this research. Interesting. So there are a lot of avenues that you can explore to better this research. For one, our paper focused on untargeted white box attacks. So I'd say if you want to add in more complications, because the real world is often this simple, right? Like you might not always have access to the model inputs or the gradients for that matter. So I think if you're a future researcher looking to work in this field and you want to improve the attacks and defense strategies for time series tasks, I would urge you to work in the black box attacks domains, where you model the deep learning model itself as a black box, and try to perform the adversarial attacks based on the outputs of the model and its predictions. And I think in the image domain, again, there's something called one pixel attack, where a group of researchers have shown how, again, it goes back to the FGSM principle, where you try to maximize the loss with like the least effort. And these people really achieved that to a great extent, where they identified like one pixel in the image that you can modify that would throw off like the model. So I'd be interested in seeing something similar to that in like multivariate time series forecasting. And that is on like the attacks front. And in terms of like the defenses though, I think coming up with better defense techniques that would help fortify the deep learning models is like another area to explore. So for example, like I told you earlier, with like the data augmentation based approach, a lot of it rested on us knowing the magnitude of perturbation, right? So can we come up with something that would help us would help us predict in real time what the perturbation magnitude is, so that the model can be more robust, instead of us having access to it in the beginning? Or there's something called model agnostic meta learning, where you can perform these defense and attacks agnostic of the model itself to any deep learning architecture. So it doesn't really matter which domain we are operating in anymore. So that's scary. But I also see like a lot of possibilities in fortification, again, when you look at it. And I think like on the defenses front, that is something that would be worth exploring too.
Very interesting. And so my final question is, what's next for your work? Are you planning on writing another paper?
I don't think I am planning on writing another paper. I'm kind of pivoting now. I think I'm done with the academia. I'd like to work in the industry, and I look forward to working on real world projects, and just applying what I've done over the years, and the knowledge I have, and solving like some real world problems. Because for me, yeah, it was nice working in a lab, but I'd like to take on like some real challenges now, if that makes sense. So I don't think I would be writing a research paper anytime soon, but you never know what the future holds.
Awesome, for sure. Great. Thanks again for coming on the podcast. I really enjoyed talking to you and hearing your opinions.
Thanks, Luke. It was nice talking to you. Thank you for having me.